I am Shebha Anandhi, a PhD student from Magnetic Materials Lab, Department of Physics, National Institute of Technology, Tiruchirappalli, Tamil Nadu, India. The title of my poster is Theoretical Evaluation of Shell Thickness on the Heating Characteristics of Fe and FeCO core for Magnetic Hyperthermia. My abstract ID is 106. The objective is to investigate the effect of shell thickness and compare the heating characteristics of Fe, Fe3O4 and FeCO, Fe3O4 core shell nanoparticles. Background. Magnetic nanoparticle hyperthermia is a cancer treatment technique that utilizes the heat dissipated by magnetic nanoparticles exposed to an alternating magnetic field. A temperature rise of up to 10 degrees Celsius from the human body temperature is requisite for killing the tumor cells. Hysteresis losses in the superparamagnetic regime, known as relaxation losses, are due to two mechanisms, Brownian and Néel relaxation mechanisms, which are based on the linear response theory. Néel relaxation is due to rotation of magnetic moments with particle when an external field is applied, and Brownian relaxation is due to rotation of the particles in applied magnetic field where the magnetic moments are coupled to the particles. The effective relaxation time tau is a combination of Néel and Brownian relaxation times tau n and tau b respectively. The power dissipation P due to the Néel and Brownian relaxation is expressed here. The power dissipation is proportional to the frequency and square of the applied field. The specific absorption rate SAR gives the magnitude of power dissipated by the magnetic nanoparticles. Iron oxide nanoparticles with various surface functionalization and substitution have been established as an appealing heat mediator in cancer therapy. However, to minimize the treatment duration and particle concentration in the therapy, highly magnetic nanoparticles such as iron or iron cobalt are preferable. In this presentation, we shall see the theoretical evaluation and comparison of SAR for iron and iron cobalt cores with the well-established Fe3O4 particles. Although Fe and FeCO nanoparticles up to 20 nanometers are realizable, they are prone to oxidation, and the heating efficiency is affected by the oxide shell. Fe and FeCO with Fe3O4 shell of various core sizes from 6 to 23 nanometers and shell thickness T from 1 to 10 nanometers at a practical applied field of 4 kA per meter and frequency of 500 kHz have been considered in the study to compute the theoretical heating characteristics. The table shows the magnetic properties of the pristine materials which were used in the theoretical simulations, where Ms is the saturation magnetization and K is the magnetic anisotropy. Figures A and B show the SAR versus particle size of Fe and FeCO cores respectively with varying shell thickness from 1 to 10 nanometers. Figures C and D show the optimum particle size for maximum SAR, d-opt in the left y-axis and SAR in the right y-axis as a function of T for Fe and FeCO cores respectively. SAR for pure Fe with a d-opt of 9 nanometer is 350 watt per gram, which far exceeds the value of 90 watt per gram corresponding to Fe3O4. Although the SAR of oxidized Fe reduces drastically about 3 to 4 times, it still exceeds the value of Fe3O4, which is promising for future applications. Similar behavior is observed with iron cobalt as well. SAR of Fe and FeCO with a Fe3O4 shell of 5 nanometer thickness reaches a characteristic maximum of 200 and 240 watt per gram respectively, which is obtained at the d-opt of 30 nanometers. This trend of FeCO giving better heat than Fe with a very thin oxide shell has also been experimentally verified. Even though the theoretical d-opt for 1 nanometer shell thickness is at 10 nanometers for the Fe core, a broad range of particle sizes from 5 to 15 nanometers can give closer SAR values of 60 to 80 watt per gram. The results suggest the validity of LRT to be applicable even to core shell particles where the Néel-Brown relaxation mechanisms of both the core and shell contribute to the heating characteristics. The scope of the theory can be expediently extended to experiments provided the control of core size between 10 to 20 nanometers and shell thickness within 5 nanometers is achieved. Conclusion. The optimum SAR for each shell thickness of various Fe and FeCO core sizes is found to increase up to an iron oxide shell thickness of 5 nanometers and then decreases further. The optima of both Fe and FeCO cores are broadened with the iron oxide shell. The linear response theory is fittingly applicable to core shell particles. Here are the references. Thank you for watching.